Welcome back to Hoffman Tactical. So today we're going to be comparing the strength of parts printed on a resin printer to parts printed on an FDM printer. So if you're not familiar with what those things are, they're both 3D printers for printing parts from digital files, but they're two very different technologies. So the thing they have in common is both of them build up parts in layers. So they start with the bottom layer and they put down one layer after the other and they stack them up until they get a finished part. That's where the similarity ends. So FDM printers are your common, low-cost 3D printer used by most people who print structural items like gun parts or AR-15 lowers or Glock slides or Glock frames, So the FDM printer works by taking, it basically has a nozzle, kind of like a hot glue gun. It melts plastic, like a filament, like weed whacker filament. It melts it through a nozzle, and it builds up one layer just by putting down little lines of plastic. Then it moves to the next layer and repeats the process. That's how that works. It's just a hot glue gun with some motors, a little more complicated than that, but it's basically how it works. Resin printers work by they have a vat of resin, and there's several different kinds of resin printers. This is just the most common one today. They all operate on a similar principle, though. You have a vat, and you have a source of UV light underneath, and it shines UV light on, for whatever shape that particular layer is supposed to be. It shines that UV light into the vat, cures that particular layer simultaneously, then it lifts up the part, puts more UV light, cures more resin, and builds up the layers by curing each layer of resin into a from liquid to solid by putting UV light onto it. The resin is cured by UV light. So UV light takes the resin from a liquid, turns it to a solid. That's how resin 3D printers work. So very different than FDM printers, which are fused deposition modeling or fused filament fabrication. Some different names for them. They're just your basic 3D printer. They melt plastic through a nozzle, while resin printers cure a UV curable resin with UV light. So those are the two different technologies. Now, generally speaking, FDM printers are lower resolution. They have much less detailed models, but the parts are stronger. You have more material options. You can print with lots of different, more exotic plastics, get impact-resistant parts, and the printers themselves tend to have, for the same price, you can get a printer that's big enough, or I should say, for a printer that's big enough to print firearms parts, they're much lower cost than resin printers are. Now, all of that is changing. So, resin printers have, generally speaking, the resins are brittle and weak, but there are now resins coming out, and there are resins that have been around for a while that are much stronger and more impact resistant. So today we're going to be testing the Siraya Blue resin, and a gentleman printed these parts for me, sent them to me to test, so thank you for sending those out and allowing us to test them, just to help give us an idea of how good resin parts are. So we're going to be testing the Siraya Blue resin, which is an impact resistant, tough resin is what they call it. There are actually other resins available which are probably even stronger and more impact resistant currently. This particular resin actually has been around for a little while. So we're going to be comparing that resin to a part printed from PLA Plus, which is eSun PLA Plus, which is the most popular filament for 3D printing firearms parts on FDM printers. So the big advantages that resin printers have over FDM printers is that they print parts that are faster and they're much higher resolution. The layers are much smaller. You can get parts that are more detailed than injection molded parts. Smooth surfaces, they make really beautiful parts. I was really blown away by the incredible detail of these resin parts compared to just the FDM parts, which are they're good enough. They work, but they're not that detailed. So without further ado, let's jump right into the testing and see which one is stronger and which one is going to have a higher tensile strength. Okay, so here is our tensile tester. Here are all of our test samples. Basically, I'm going to load the samples into the jaws right here, where it'll pull them apart with a stepper motor up here and a lead screw. And then we have a load cell down here at the bottom, which records the force and sends that data to the computer. Okay, so we're going to start with the resin prints. And these are vertical test samples. Do the horizontal ones next. Full 121 pounds, by the way, guys. That's 421 pounds is what one of these things held up to. That's pretty impressive. I can't give you the PSI number off my top of my head, but we'll find out a little bit later. Let's break another one. Let's make sure it's in there. Wow, almost 450 pounds. That's all my machine can pull, by the way. So this is getting a little bit on the edge here. It's right on the edge of what I can test with this size of test sample. By the way, the ambient temperature is 75 degrees Fahrenheit. 438 pounds. Let's see. That one broke at 421 pounds. Okay guys, here's some of the data. I'm just going to show you real quick. We'll look at it better later. 8,500 PSI, almost 8,600 PSI was our tensile strength in the vertical dimension. That's extremely good for the vertical dimension. Stronger than any FDM part I have tested. And then the graph is also really interesting. You can see right here, you kind of go down, there's a little peak there, then it drops off before suddenly snapping. That means the part started to yield a little bit before breaking. So it's actually, I don't know if ductility is the right word, but the part kind of stretched and yielded a bit before snapping. So it's not super brittle. That, guys, is really cool. Okay, so now we're going to do our horizontal resin test samples. So these ones are printed horizontally on this surface. So let's see how these compare to the vertical samples. So let's get that loaded in there. These are a bit more tricky to keep lined up. Let's pull it. These have half the cross section, by the way, of the vertical test sample, so they should break half the weight. 154 pounds. And 125 pounds. That one was low. Okay, so weird data here. So it was significantly less than the vertical test samples, which is really kind of strange because horizontal ones are normally stronger because of the layer orientation. Though obviously layer orientation is not that important with resin prints. Not important at all. Now looking at the chart here, you can see that the strong sample right here had quite a bit, had a nice yield point, I should say. It's not, ductility is the wrong word, I believe. It yielded nicely and then finally broke. All the samples did that to a more or less degree, very slightly, with the exception of number E right here, which is snapped off. My guess why this strength of the horizontal test samples is less than the vertical test samples is probably because the parts were cured differently. He probably printed them at a different time and cured them differently. Okay, you guys know what's next. What's next is the eSun PLA Plus. Just for fun, we'll do the horizontal test samples first. So we'll load this in there. And into the jaws, the holders, and we'll snap it off. Okay, so here is a quick shot of the horizontal test samples printed from the eSun PLA Plus. We actually were just under 9,000 PSI, which is really strong. That's actually up there as far as strength goes with prints. 8,900 is really, 8,936 is really good PSI-wise. And then if we look at our break here, you can see we yielded right here, and it actually yielded quite a bit more than the resin prints, though not that much compared to other plastics you can print with on a FDM printer, but it did yield nicely, so only one of these breaks was pretty sudden, and even that one yielded a little bit. So let's move on to our vertical test samples. Okay, this is where the rubber really meets the road, so we have a bit of fuzz on there. It shouldn't affect anything. This is where FDM prints really have a problem. So we're going to pull this guy. £289, so not that good really. We'll look at the data later. 100 pounds, 309 pounds, 200 pounds, 291 pounds, and it snapped off. Okay, so here's the results from the test with the vertical test samples, these little fellows, and we only got about 6,000 PSI tensile strength, which is not the best compared to what we did today, but it's actually still pretty good. And you can see the chart right here. We did not have any yield at all. The parts just snapped right off. This is true for almost every single FDM material out there. Okay, now let's look at the data. So this chart right here is comparing the average tensile strength in PSI of the different samples we tested. So of each sample we had 5 different samples in each category here, each column. I just took the average of the peak force on each one, so the point where the plastic yielded, and I took the average force, calculated the tensile strength in PSI using the cross section, and this is the result. So resin is on the left, PLA Plus is on the right. The blue samples were the ones printed horizontally, and the red ones are printed vertically. So right away you can see that the strength between these two parts is very similar between the PLA and the resin. But what's quite stark is that the PLA part, the vertical test sample, is significantly weaker than the horizontal test sample. That's normal. That's because that's the layer orientation direction, and layers tend to not be as strong as the actual material strength, which is what the blue column is. We come over here to the resin side of things, and the opposite is true. Vertical test sample is significantly stronger than the horizontal test sample. I don't know why this is. This shouldn't be the case. In theory, resin, I forget the right terminology, but resin prints should be the same strength no matter what the orientation. They're kind of like an injection molded part that way. It just makes a solid piece of material, and it should be equal in horizontal and vertical. In this case, it was not close to being equal. The horizontal part was much weaker. Why was this? Probably because the part wasn't as cured as much, or it was printed differently than the horizontal part. I'll email the gentleman who sent me this and try to determine if that is the case and try to work that out. But for more testing is really needed to know for sure what's going on there. But what is interesting is that the resin print was so strong in the layer orientation direction. What that means is if you are printing a part from resin, you won't have to worry about print orientation like you do when printing from a material like PLA Plus on a fused filament printer. And the next chart, I'll illustrate this more, what I'm kind of talking about, but the resin print is equal. It's stronger in the layer orientation direction, so printing a lower receiver at 45 degrees, for example, would actually be no problem compared to printing from PLA Plus, where printing at 45 degrees, you get significantly weaker part because of the layer orientation. So that's kind of interesting, but just looking at this data here, even though we have this strange discrepancy where they're kind of reversed and the horizontal sample is weaker than the vertical sample with the resin, they're still very comparable in strength, and the resin printer might be a little tiny bit weaker, the resin part, than the PLA Plus part. But they're actually pretty comparable and would probably be interchangeable strength-wise in applications. Let's jump to the next chart right here. What this is this is the raw data from the tensile tester machine. So in our vertical column right here, in our y-axis, we have pounds force, and down at the bottom here is displacement or time. I'm not going to assign it any units right now, but basically the further to the left, the further to the right we go on this chart, the more time passes, and the more time passes, the further the part is moved. Time equals displacement. They're linear in this case because we have a stepper motor running at a constant speed. So you can see the resin prints are the ones over here that broke way over here on the right side of the screen, and then the PLA Plus prints broke here on the middle part of the screen. Something to keep in mind is the horizontal test samples, which are the yellow and orange lines. Those broke a lot lower than the vertical test samples just because they have half the cross-sectional area. So they're actually stronger horizontally. Let's say the PLA Plus, for example. The yellow line here, it comes in as being lower than the gray line, which is the PLA Plus vertical sample. It's actually a lot stronger than the vertical sample, but because it has half the cross-section, the little horizontal print, it comes out with less pounds force. But the actual PSI strength is more, just because of the cross-section. So just don't let that confuse you. So looking at this chart, you can see that the PLA Plus vertical test sample is very rigid. It's got a steep line, and you can see that the horizontal test sample printed from resin was actually quite flexible, and it appears that it stretched quite a bit before finally breaking. Now, if we look at the PLA Plus vertical test sample right here, you can see that it had no ductility. I don't know if ductility is the right word, but it didn't yield at all. It just stretched right to the moment it snapped like a piece of glass, a glass rod, bang, it broke, and right there it dropped right off. So it was pretty brittle in the vertical axis. The PLA Plus horizontally, you can see it yielded, and then it just kind of slowly dropped off and then kind of broke very gradually. It was not a sudden break, and it was a nice controlled, easy break. This is ductile. This is a good way of breaking. The part did not fail suddenly and spontaneously. Now, if we look at the resin prints, both of them actually failed pretty much the same way. Now, the horizontal sample is much less, so you can't see it as much, but because it's a much lower amount of force because it had a smaller cross section. But both parts kind of came up, they peaked, they yielded, and then they spontaneously broke at the end. So it's kind of a mixture between the vertical and horizontal PLA test samples. So they did have some yield to them, but they did not continue yielding. They ended up at the end breaking in a brittle way, kind of like a piece of glass would. And I can illustrate that here with some video overlays. The PLA, when it breaks, just kind of softly breaks, and the resin print shatters almost. So it is a bit more brittle than the PLA is, and it's probably not as resistant to impact, but I can't tell you for sure because I haven't actually done any real impact testing with an impact tester. But just looking at this data here, the resin prints have some ductility and they're not incredibly brittle. Incredibly brittle is the vertical test sample from PLA. Okay, let's move ahead to our next graph, and this is where we'll look at strength. So here I have compiled all of the filaments which I have tested, and all of these are tested using the same testing methods. The print settings are all the same for all of these. It's just the temperatures and filament specific settings that have been changed. So you can see this is the same as the last chart. We have blue is horizontal and the orange or red is the vertical test sample, and then this gray line right here is the average between vertical and horizontal test samples. And I have sorted these materials by that average, and I've done that because some filaments are a lot stronger in vertical and weaker in horizontal, or vice versa, and I thought this was a good way of sorting them. So you can see that the blue resin test sample and the eSun PLA Plus kind of fall right here near the middle, and they're once again very, very comparable. The eSun came out a tiny bit on top on the average, but I think if you tweaked how you printed the resin print, you could get that quite a bit higher. So strength-wise, the resin print's actually doing pretty good. Now we can look at some of the other filaments here. The absolute strongest filament I have ever tested is Prusament PLA, and it is all the way over here. It's extremely strong in actually both layer adhesion and horizontal dimension. It does tend to be brittle, of course. It's got almost no flexibility and it snaps and shatters. But if you look at the tensile tester machine, the jaws or the holders that hold the test sample undergo a huge amount of stress. And I have printed those parts from Prusament PLA because it's the strongest filament that I have currently. And it's the strongest in both dimensions. What's interesting here is if you look at the resin sample, in the vertical dimension, the resin sample is actually significantly stronger than the Prusament PLA, which is really interesting. So the resin has excellent layer adhesion and really strong in that dimension, stronger than any of the FDM parts tested here. So the resin definitely has potential. Okay, let's try to summarize things a bit. Thanks for sticking with us this far through the video. So from looking at those results, the resin and the PLA Plus were very comparable in strength. I would have to say structurally, the resin, in actual tensile strength, the resin is going to have a little bit of an edge because the layer adhesion is so good and because it maintains its ductility. Even though it doesn't have that much ductility, it maintains the ductility no matter what the layer orientation is. Unlike the PLA Plus, which will break in the vertical test sample. The layer adhesion direction on the PLA Plus is not ductile and will break in a very brittle way compared to the horizontal dimension, while the resin print is equal no matter what the orientation. Now the strength of the resin print was very slightly less than the PLA Plus if you take the average between the vertical and horizontal test sample, but I think that horizontal test sample was weaker than it could have been if it was printed a little differently. So I think strength-wise, the resin prints are probably a little tiny bit better. So strength-wise, resin is definitely strong enough to print firearms with. Now, it was a little more brittle than the PLA Plus was, but I don't think it was that much more brittle. So how much more brittle the resin is, I really can't say without having a proper impact tester set up, but it wasn't that much more brittle than the PLA Plus. So I think structurally the stuff is very sound. Now there's one thing I didn't test today, and I have not seen any testing on it. That is the thermal characteristics of resin prints. What is the heat deflection temperature of resin? I don't know. So I heated a piece of it up with a lighter just kind of to feel what it did. It didn't melt. It actually just got kind of crumbly and broke apart with my fingernail while it was still hot. And then once it cooled down, it restored to what appeared to be its previous state. But I don't know what that temperature was where it got weaker. So the heat resistance of parts printed on a resin printer is right now still completely unknown. So that's something that really needs some investigation, and that would be an important factor deciding whether you use a resin printer or a standard fused filament printer. Another important note is that the Siraya Blue resin I used is not the best resin out there. This is the stuff I tested that the gentleman printed for me. There are other resins out there which are more impact resistant and possibly stronger. One of them is the frozen green nylon-like resin that they have, and that one is quite impact resistant, though I haven't actually done any testing with it. So there are better options out there, and there are always new resins coming. So resin prints are definitely getting better. So would I recommend you buying a resin printer instead of a fused filament printer? Right now, I would not, unless you're just wanting to experiment. If you want to be able to successfully print firearms, resin printers right now are still experimental and they haven't been proven like fused filament. A fused filament printer will work for you. An FDM printer will work. It's already been used. I've used them. They work great. So that's definitely going to function. Getting a resin printer is still experimental, but I think there's a really good chance that it will work out for you. Now, resin printers are a bit more expensive to get one big enough, and you have to get the proper chamber set up for curing the parts in UV light after you print them, and of course for washing them before that curing process. So it is a different process, a little bit more involved than fused filament printing, but structurally I think you can get parts out of a resin printer once you get your setup done that are as good as parts out of a fused filament printer, possibly slightly more brittle. But right now, resin printers are looking better and better. So stay tuned for more. Hope you found today's video helpful or at least interesting. We'll be doing more testing videos in the upcoming weeks, so stay tuned for that, and I'll see you guys again then.